Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know, within this module we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module we are currently on the fifth topic, that is time sharing. So within this topic, we are talking about the concept of time sharing and how it is implemented, right? So time sharing, as we know, is a concept where the operating system shares the CPU time among multiple processes so that we as users are able to run multiple programs on a limited number of CPUs, right? And we have talked about this, that time sharing is implemented using this concept of CPU scheduling, right? So CPU scheduling is essentially a resource allocation technique in which the operating system allocates the CPU, which is the resource, among the multiple processes, right? And we have been trying to understand CPU scheduling. So we have been trying to answer different questions related to CPU scheduling, right? For example, in the previous videos, we have talked about why we are doing this, how we are doing this, basically what is the mechanism via which the CPU scheduling is implemented. Then in the last video, we talked about when, that is, when can the operating system schedule the CPU, at what opportunities or time it is a good idea to schedule the CPU, right? So now in this video, we are going to talk about the next question, that is who. Who is responsible for doing this scheduling, and what are the responsibilities that the entity which will be doing the scheduling, basically the CPU scheduler, right? What are all the things that the CPU scheduler does, right? We will be talking about all these things, right? So without further ado, let's get started. So let us start the discussion from this slide. In the previous videos also we have seen this. So basically in this entire topic, we are trying to understand CPU scheduling by answering different questions or understanding different aspects about it. So in the previous videos, we have understood why we are doing this, how we are doing this, and when can we do this, right? So in this video, let's focus on this question, that is who is responsible for doing this CPU scheduling, right? So the answer is that there is a component inside the operating system, a software component that is known as the CPU scheduler, that is responsible for, that piece of code is responsible for doing this scheduling, right? So this is the CPU scheduling diagram that we have already seen. So let me go over this once again. So as you can see, this is the CPU, and this is the time this is the CPU time, right? And as we can see, CPU time is being shared between different processes. This is the time sharing, right? And to share the CPU time, we have to switch between different processes. So the key idea in CPU scheduling is to have a mechanism to switch between different processes and select the processes properly, right? So if you look at this switching, you can see there is some process A, and then we do a context switch, that is switch between two processes. And after that, there is some other process that is running. And we said that during this context switch, there are a few things that needs to be done. The first thing is that we must transfer the control from the user process to the operating system, because without the control of the CPU, unless the operating system is running, it won't be able to do the CPU scheduling. So the first step in CPU in context switch is to transfer the control of the CPU to the OS. Then the next thing is that we have to select the next process. This is an important part, right? So before we switch to some other process, the operating system has to first of all select which process should be assigned the CPU, right? And this selection is quite important. So it's not that the operating system can just select any random process. It has to keep in mind the overall goals of the system. It has to like there are several different criteria, right? The system should be overall responsive. So it has to give time to all of the processes, right? Each process should get a fair share of the CPU, right? So all of them must get some response from the operating system. Then throughput is also important. We must be able to finish as many jobs as we can within a given time frame. So we will study about these different criterias, these different goals for which the operating system tries to optimize while making these scheduling decisions. So the point that I want to make here is that this decision is quite important, that is which process should be assigned the CPU next, and this decision is taken by the CPU scheduler, right? The scheduler is a very important piece of component that is responsible for doing all of this. This decision is based upon some algorithms that we call as scheduling policy. So the next topic, the entire topic, is dedicated to studying different types of policies that the scheduler uses, right? So once the selection is done by the scheduler, then we do the actual switching. In this step, we switch the registers, right? We save the registers of the currently the previous process, right? In this case, process A, and we restore the registers and state of the next process that has to be executed. And once that switching is done, the control of the CPU is transferred to the next process, and thus the context switch is complete, right? So in this overall thing, the scheduler is responsible for selecting the process and then switching the process from one process to another, right? So let's talk about the scheduler and what are all the things that it does. So this is the again, this is also depicting time sharing in a different way. So you can see here we have the CPU, and there are several programs or processes. We can say there are several processes that want to execute on the CPU, right? And inside the operating system, there is this scheduler. So the question is that who will select, who does this selection? So what selection? Basically, out of all these processes that are ready to execute, that want to execute on the CPU, which of the following will get the control of the CPU? This decision is taken by the scheduler. Here there are two decisions actually. The first decision is that whether should we switch or not, right? So depends on whether the scheduler is preemptive or not. So the point here is that when the control is given to the operating system, right, it might be the case that the current process which was executing, it has more instructions left to execute, it has not finished execution. So it can, if we give the control of the CPU back to that current, back to the process which was running, then it can very well continue execution. So when the control of the CPU goes from the currently running process to the operating system, there is a choice or there is a decision that the scheduler has to take. That decision is whether should we switch from one process to another or allow the current process to continue, right? So this is the first decision, whether to switch or not, right? And depending on whether the scheduler is preemptive or not, it will take that decision. If the scheduler is a preemptive, if is following a preemptive scheduling policy, then even when the process has execution left, it will switch to some other process. We have talked about non-preemptive versus preemptive approach in the previous video also. So in the non-preemptive approach, the scheduling happens only when the process can no longer execute further, right? It could be because the process has terminated and has no more instructions left to execute, or it could be the case that the process has blocked, it is waiting for some event to happen, and even if you give the CPU, it will not execute instructions. So if the scheduling happens only when the process cannot execute any further, this is known as a non-preemptive scheduling policy. We have talked about this, right? Whereas in the alternate way, in the contrast is that if the scheduling can happen anytime the operating system gets the control, right? There are several moments when the operating system gets control. Like once the two cases that we discussed just now, like when a process terminates or when a process blocks, apart from these, a process can be interrupted due to a device interrupt or a timer interrupt. A process would be making system calls during its lifetime, right? So there are several cases or several time instants when the control of the CPU goes to the operating system. So if the operating system decides to switch from one process to another, even when the current process has not finished execution or is not blocked, that is, if you give the control and it can very well continue execution, then that is a preemptive scheduling policy, right? So before the scheduler can decide to which process should the CPU go to, first of all, it has to decide whether to switch at all or not, right? The operating system can very well choose that it does not, it will not switch and give the control of the CPU to the currently running user process, or it can decide whether it can also decide to switch the currently running user process, even if it can continue execution in case of the preemptive scheduling policy, right? So the first question or the first decision during scheduling is that to switch or not, right? To give the control to the current process or to a different process, right? The second decision is that if the scheduler decides to switch, right, then to which process should it switch, right? If it is following, let's say, if we have, let's say, we get the control of the CPU, and it could be the case that the current process can no longer execute, or the current process can execute, but still we are deciding to switch, as in the case of a preemptive scheduling policy. In that case, the next decision is that now out of all the processes that are ready to execute, to which process should the control of the CPU be assigned, which is the best candidate, and according to some criteria, which is the best candidate process to which the control of the CPU should be given to. So this decision is dependent on several algorithms, which we call as scheduling policy. So the scheduler inside the CPU follows some kind of scheduling policy, which is an algorithm which is trying to optimize some criteria. It could be throughput, it could be response time, or a combination of several different criteria, so as to give a good user experience, right? So each operating system has some kind of goals for the user or the machine it is trying to manage, right? And depending on the goals, there are certain algorithms which we call CPU scheduling policy, and we'll talk about these different policies in the next topic in detail, right? So the point is that the decision as to which process will get the control of the CPU is based on the scheduling policy. So to summarize, the component there is a software component inside the operating system which is responsible for doing CPU scheduling. And while making scheduling decisions, there are two decisions. First of all, the decision is that whether to switch or not. That is, the first case is that give the control back to the process which was already currently executing process, or the other alternative or the other option is that to switch to a different process. So the first decision is that whether to switch or not, right? And the second decision is that if we decide to switch to a different process, which is the best candidate process to which the CPU should be assigned. And this decision is based on some algorithm that we call as CPU scheduling policy. So this is the role of the scheduler at a very high level, right? So now let us delve a bit deeper into how does the scheduler work. So now we are going to see how does the scheduler actually work. To explain that, let us go back to the process state diagram, right? So this is the process state diagram, and we have already talked about these in the earlier videos. Let me quickly recall about the this life cycle diagram. So this diagram is basically, it is depicting the life of a process, right? It is showing what are all the different states between which a process can transition through its lifetime. So each process starts from this state, that is the new state when it is created, and then it is put into this ready state. In the ready state, this indicates that the process is ready to execute, but it is currently not executing. It is waiting for the CPU, right? Then what the operating system does is that it picks that one of the ready processes, and it is basically the scheduler that picks the ready process, the next ready, like the scheduler makes this choice, right? It picks one of these ready processes and assigns it to the allocates or schedules it to run on the CPU, and that is when it goes to the running state. So in the running state, the process is basically executing the instructions and performing the computation that it is supposed to do, right? Now if you look carefully from the running state, there are three options that a process has. The first option, the simple one, is that it could be the case that the process has executed all of its instructions and then it terminates, right? It was running, it finished all of its instructions, and then it got terminated. In this state, the process has finished its execution and all of its resources are deallocated. Now there is another case in that the process could block because it needs to wait for an event, and that is when it goes to the waiting state. So in the waiting state, here the process is waiting for some kind of event to occur, and here the process has been blocked. Even if you give the control of the CPU to this waiting process, it would not execute further instructions, right? For example, if a process is waiting for some data to arrive from some input device, unless the data arrives, it cannot process that data, right? It cannot continue further execution. Or a process could be waiting for some resource which is currently unavailable, or it could be waiting for its child process to terminate, right? There are many reasons why a process would need to wait, but the common thing is that if it is waiting for an event, it cannot execute until that event happens, right? It is blocked. So that is when a process waits and it is in the waiting state. Eventually that event for which the process was waiting happens, and then it transitions from waiting to ready state, right? So again it is ready, and if you give the control of the CPU to this ready process, it will start executing instructions in the running state. So this was one kind of cycle, that is running, waiting, ready. Another cycle is that the process can go from running back to ready state if it is interrupted. It could be interrupted due to some device interrupt or a timer interrupt, right? And it goes back to ready state. Even if it is like here, it is ready to execute instructions, but the control of the CPU was taken away from it due to some reason. So this was a brief recall of the life cycle of a process. Here, using this life cycle diagram, we are going to understand the working of the scheduler. So the first thing is that the scheduler maintains certain data structures to keep track of the different processes. So let us first look at those data structures. So these are basically scheduling queues, right? So let's start with the ready state. As you can see, the scheduler will pick a process from the pool of ready processes, right? If you look at the scheduler, then from what all processes it is making the selection for the next process that will be allocated to the CPU. So my question is that from which state it is selecting its candidates. It does not select its candidate from any other state except for the ready state. A new process is not selected, neither terminated or running or waiting. Only the processes which are in the ready state, they are chosen for, like, they are considered for selecting the next process which has to be assigned the CPU, right? If a process is already in the running state, it will not be considered. If it is in the waiting state, even if you give the CPU to that process, it won't execute instructions. In terminated state, there is nothing to execute. In new state, it is not yet ready. So only from the processes which are in the ready state, only those processes are taken into consideration while selecting the next process which will execute on the CPU. Now, all of these ready processes, right, the pool of ready process that we talked about, these ready processes reside in a queue called the ready queue. This is the data structure that I was talking about. So let's say there is a hypothetical computer system and it has three processes and all of them are ready to execute. So all of them will be stored in a queue data structure which is known as the ready queue. And the scheduler will pick one process from the queue for executing on the CPU. And this queue need not be a first in first out queue. Any process could be selected based on the scheduling policy, right? Now the next point is that the ready queue is generally implemented as a linked list, right? It could be implemented as some other data structure also, but generally it is a linked list. And what is stored in the linked list? How do you store a process in a linked list, right? You actually store the process control block of that process into the list. So we have already talked about what is a process control block. Process control block, or PCB for short, is a data structure which stores all of the information that is necessary to describe a process, right? All of the information that is related to a process, that is stored in this data structure. It is generally a C style structure, right? As you can see, struct proc, and this contains all of the information related to that process. This is how we describe a process. And when we are storing several ready processes, we are actually storing the PCBs of these ready processes in the ready queue. So this was about the ready queue, right? Now, apart from the ready queue, there are other queues also in the computer system. As you can see here, there is a set of wait queues, right? A set of wait queues also exists for processes that are waiting for an event, right? So, as I talked about this earlier also, very often during the life of a process, it has to wait, right? And when it is waiting, it is not in the ready queue. It is put in some other queue, which is called the wait queue. Why this is the case? Because in this queue is meant for a special purpose. Only those processes which are ready to execute will be stored here. And the scheduler will use this queue for selecting the next process for execution. So if any process blocks or if any process goes to waiting state, it moves from this queue to one of these wait queues. Why there are different queues? Because there could be different reasons for which the process is waiting. So let's say uh, there are three resources in the system. Just for example, there are three different resources in the system. One is a hard disk, one is a printer, and let's say the other is the display, right? And each of these processes are waiting for some resources. So these two processes are waiting for the printer, these three processes are waiting for the hard disk, and these two processes are waiting for the display. So all of these processes are waiting for different things. They are waiting for different resources, and the resources are limited. That is why they are waiting. So we maintain different queues for different purposes, right? So there are so many reasons for which a process could wait, and there are separate queues for each of these, right? So there is a set of wait queues apart from this ready queue, and it could not, these ready queues, it is not necessary that they would just be for resources. They could be for other reasons also, like there could be a queue where the processes which are waiting for the child process to finish. There could be a queue for some IO operations to finish, right? There could be many different queues, but the point is there is only one ready queue, and in that ready queue all the processes which are ready to execute are stored, whereas other processes which are blocked are stored in this set of wait queues, right? So this was about the different data structures, basically the different scheduling queues that exist. One is a ready queue, and the other, there are several wait queues also in which the process wait for some event to happen. Having understood these different kinds of queues, let us see how the scheduler uses these queues and to make scheduling decisions, and how processes move from one queue to another during their lifetime. So now we will take a working example, and through this example, we will see the work, like how the scheduler works, right? So in this example, I have taken a hypothetical system where there are only three processes, right? And you can see when a new process is created, it is placed in the ready queue, right? So first of all of these processes would have been created, and once they are ready to execute, they are placed in this ready queue, right? So this is the pool of processes which are ready to execute. If you give them the control of the CPU, they will start executing instructions. So first of all of the processes after creation enter this queue. Now let's see what happens next. The next thing is that the scheduler picks a process from the ready queue and runs it on the CPU, right? So out of P1, P2, and P3, in this case, you can see that the scheduler has picked P1 and allocated the CPU to P1, and P1 is now in the running state. So P1 is basically executing its instructions, right? So now let's see next. The next thing is that let's consider the case that P1 has to wait for some kind of event. So as you can see, at times the processes need to wait for some kind of event, and when that happens, they block themselves and wait in an appropriate queue, right? So let's just assume that P1 has initiated an input operation. It wants to read some kind of data from the hard disk, right? So for the time being, until the data is not read, right, it will take some time to read the data. So we comparing the speed of the hard disk with that of the CPU, the time that it will take to read the data would be a few milliseconds, right? In the time being, the CPU can execute other process, right? So the speed of the CPU is much more than IO devices, and it should not be left idle. So what happens is that the process P1, when it is waiting for the data, it gets blocked and it sits in a queue. Only when the data will be available after a few milliseconds, then process P1 would be able to execute further instructions. Even if you give the control of the CPU to process P1, it cannot execute because further logic depends on that input data, and that input data is not yet available. It would take a few milliseconds, right? So process P1 is waiting on in one of the wait queues. In the meanwhile, during the time the data is being read from the hard disk, here other processes will get to execute on the CPU, right? So let's see next what happens is that the scheduler picks process P2 to run on the CPU. And after this, let's assume that the event for which the process P1 was waiting has finished. So basically, it was waiting for the input data to be read from the hard disk. Let's say that input operation is done. When that is done, process P1 is now ready to execute. Right? When the event for which the process was waiting occurs, it unblocks and moves to the ready queue. So process P1 had initiated an IO operation, basically a read operation, input operation on the hard disk. That data took some time to be fetched. Once that data is fetched, the process P1 can continue its execution, but it won't be given the control of the CPU directly. It moves from the waiting to ready state, right? So it will move from this queue to the ready queue. So I'm trying to explain how the processes are migrating among the queues, right? So P1 went from ready to running state, and from running state it went to the ready queue, sorry, the wait queue. Once the event for which it was waiting happened, it moved from the waiting queue to the ready queue, right? So now let's see what happens next. Currently P2 is executing on the CPU, it's in the running state. Now it could happen that there is a timer interrupt and the current process is preempted and moved to the ready queue. So we have talked about the case that when a process is executing, it could be interrupted, right? It could be due to some device interrupt naturally, or it could be due to some explicit timer interrupt also, right? But the point is that no process will be allowed to execute for an indefinite amount of time in a system where preemptive scheduling policy is followed. So what is preemptive scheduling policy? We have already talked about this. So in preemptive scheduling policy, the operating system can switch to a different process even if the current process has instructions left to execute. So in this case, process P2, we are assuming that process P2 had more instructions left to execute. It was also not in any way blocked. So if we are taking the control of the CPU from this process, we are like preempting the process from the CPU. So all modern processes follow preemptive scheduling policy, and no process is allowed to run for an indefinite amount of time. It will either get interrupted naturally or there could be a device interrupt. In that case, the transition that I'm going to show that is interesting is that it moves from the running state to the ready state and it goes back to the ready queue. So there are two types of cycles that you should focus. One is that let me go back. So the one cycle that we saw is that process P1 went from ready to running, and from running it blocked itself, so it went to waiting state, and from waiting it went back to the ready state. So this is one cycle: running, waiting, ready, running, waiting, ready. So a process could cycle in this way, that is, it gets control of the CPU, then it blocks, then it unblocks, and again it gets to execute on the CPU. The other kind of cycle is the one between ready and running state. So here you can see process P2 is allocated the CPU. Then after some kind of interruption, it goes again back to the ready state. Again, it is, so it could be a combination of these two also, right? One process can go from waiting to ready or from running to ready. Anything can happen. But the point is that during its lifetime, a process migrates between these states. And when it is migrating between these states, it moves from one queue to another. Sometime it will be in the ready queue, or there will be sometime it will be in the running state. So for running state, there is no queue, right? Only one process can run on the CPU at any given point in time. So there is no queue for a process which is in the running state. It's just a state. But for ready and waiting, there are queues. And during their lifetime, the process cycle between these states and they move from one queue to another, right? So this is how the processes behave. And now let's see some more examples. So let's say process P3 is allocated the CPU, so it moves from ready to running state. And then let's say there is some kind of interrupt and it goes back to ready state, right? So this is the cycle between ready and running. Here the process is not blocking itself. It just got preempted from the CPU because there was some kind of interruption from some device, a normal device or a timer also, right? So this is one kind of cycling. The other is the one which involves the waiting state. So let's say again process P2 is selected and it goes to running state, and then it blocks due to some reason. And once that event for which, so when it is blocked, the CPU will be allocated to some process, let's say P3, and then after some time we see that P2 gets unblocked and moves to the ready queue, right? So this is how processes migrate between different queues. And the role of the scheduler, right? The role of the scheduler is that it maintains these data structures, and whenever there is the time comes, it selects one process from the ready queue and like allocates the CPU to this process, that is schedules that particular process on the CPU, right? And finally, once a process has finished execution, it terminates, right? So when a process terminates, its process control block is removed, all of its resources are deallocated, and it will be removed from all of the queues, right? So you can see in this case, process P3, now it got terminated. So all of its resources will be deallocated, its PCB will be cleared, it will be removed, and if it is in some queue, that PCB will also be removed from all of the queues, right? So this is how the processes behave during their lifetime. So to summarize, a process when it is created enters the ready queue. Ready queue maintains the pool of all the processes that are ready to execute, right? And from this ready pool of processes, the scheduler makes the decision as to which process should execute next on the CPU, right? The scheduler will always pick a process from the ready queue only, not from any other state, not from any other queue. Then the process which has been picked from the ready queue executes instructions on the CPU. It is in the running state. Now from the running state, either it could cycle through the waiting state to and come back to running. That is, it could block, then unblock, and then get scheduled, or it could cycle between running and ready. That is, it was running, then it gets interrupted, then again it can run, it gets interrupted, or it could be a combination of these two cycles. That is, once sometimes it blocks, sometimes it gets interrupted, right? The point is that the process keeps cycling between these states. Sometimes it blocks, goes to waiting, unblocks, or sometimes it's just get interrupted and moves to ready state. Finally, out of after some time, it's all of its instructions will get executed and it will terminate. And when it terminates, the process control block will be deallocated, all of its resources will be deallocated, right? So you can see how the processes behave. And in all of these, the important part to note here is that the scheduling queues are maintained, the ready queue, the set of queues, and the scheduler is aware of the states of different processes through these queues, right? So it is easier for the scheduler to make scheduling decisions, right? It does not have to consider the processes which are in the waiting queue. It will never select any process which is in the ready in one of these waiting queues for like scheduling to the CPU. It only has to consider the processes which are in the ready queue, right? So this is how the data structures are maintained, the queues are maintained, and the scheduler can select the next process that has to be assigned the CPU using the ready queue, right? So guys, this was it for this video. Thank you very much for watching. And in this video we described how the scheduler works, right? We discussed the different scheduling queues. So first of all, we discussed that there are two decisions to be made. So whether to schedule or not, and if the decision is to schedule, then to which process to perform the scheduling, like to which process to assign the CPU. Then we talked about the different scheduling queues, the ready queue, the set of wait queues. We also took an example and saw how the processes migrate between different states, move through different queues until they terminate, and how the scheduler picks one of the process from the ready queue to run on the CPU. So guys, this was it for this video. Thank you very much for watching. I will see you in the next video. Thank you.